guys, welcome back to an episode of meded.pearls, where we provide pearls for the steps, boards, and wards. Here's your pearl for the day. Does acid base cause some tension for you? Well, don't fret. Let me break down how I look at acid base problems, and we'll also do a sample problem at the end of this video. So how to break down acid base questions. I always have 5 things that I always look for. One is I'm going to look at the pH. So the pH here, I look if it's less than 7.4, that's an acidosis, and if it is more than 7.4, then it's an alkalosis. So first step, always look at the pH, and you decide whether the primary disorder first is an alkalotic disorder or an acidotic disorder. Then I look at the bicarb and to try to determine whether the acidosis or alkalosis is due to a metabolic cause or a respiratory cause. I end up looking at the bicarb and seeing if it's an acidosis, then I would expect my bicarb to be low. If it's an alkalosis, metabolic alkalosis, I would expect my bicarb to be elevated. After that, I'm going to look at the anion gap. For any acid base or any BMP that is given, always check an acid base. You'd be surprised how many hidden acid base disturbances there are even in a normal blood gas. Then I look for compensation, and I'm going to go over these equations here for compensation. If I have a metabolic acidosis, my expected PCO2 is equal to 1.5 times the bicarb plus 8 plus or minus 2. Now the bicarb that I get is, I always rely on the bicarb on the BMP, on the chemistry. That's more accurate than the bicarb on the blood gas. So I can always see what is my expected PCO2, and then I look at the PCO2 that's given to me on the blood gas, and I can see now, is my expected PCO2 lower or higher? So if I'm given a value that's higher, I have a concomitant respiratory acidosis problem. If my PCO2 is lower than what I'm expecting, then I'm going to see that there's a concomitant alkalotic process going on as well. If I have a metabolic alkalosis, here I'm looking at the PCO2 is equal to 0.6 times the change in bicarb from 24. Whatever value I get there, I subtract that from 40, and that's my expected PCO2. What if I have a respiratory problem? Well, I like to use the 1, 2, 4, 5 rule. So I have acute compensation and chronic compensation. If I have a respiratory acidosis, for every CO2 that is increased in 10, for every 10 in increase in CO2, my bicarb goes up by 1 if it's an acute compensation, or by 4 if it's a chronic compensation. And if I have a respiratory alkalosis, for every 10 my CO2 comes down, my bicarb goes down by 2 in an acute process. Chronic, every 10 my CO2 goes down, my bicarb goes down by 5. These are some helpful equations to memorize, but if you're strapped for time, I would really definitely memorize the Winter's formula, which is the compensation of the metabolic acidosis. But these compensation formulas are handy to have in the back of your pocket, so you can try to see if there's any compensation going on, or if there's another acid-base disturbance going on. Last but not least is the delta-delta gap. Now, this one, the delta-delta ratio, I have an asterisk here because you only do that if you have a high anion gap metabolic acidosis present. And what I end up doing is, easy way that I look at it is, I take the change in the anion gap. I like to use 12 as my normal. So whatever the anion gap is, subtract that from 12, that's my change in anion gap. What I do then is, I add that to the bicarb, and if this sum is going to be greater than 24, that's a metabolic alkalosis. If it's less than 24, it's a non-anion gap metabolic acidosis. Okay, so these are the 5 rules that I look at whenever I try to break down an acid-base question. I know it's a lot to process, but you just do repeated problems and you'll figure it out on your own. Now, why don't we take these equations and take this knowledge that we have and break down and use that to solve a problem? So here, I'm given that I have a pH of 7.5 with a carbon dioxide of 53, and I have a BMP. Sodium is 134, potassium is 2.8, chloride is 83, bicarb is 42, BUN is 33, creatinine is 1.2. So let's go ahead. Step 1, I'm going to look at my pH here, and the pH is 7.50. It's more than 7.4, so I have some type of alkalosis going on. Number 2, now I want to go ahead and look at the bicarb and see, is this a metabolic alkalosis or a respiratory alkalosis? So my bicarb is high, and if it's a metabolic alkalosis, I would expect the bicarb to be high. So I have a metabolic alkalosis over here. Okay, so that's my first problem here. Third, I'm going to go ahead and calculate the anion gap. So I have 134 minus 83 minus 42. The formula for anion gap is going to be sodium minus my chloride minus my bicarb. So 134 minus 83 minus 42 is 9 here. So I have no gap. So therefore, I don't need to check the delta gap. Now let's go ahead and look at for the compensation. So I'm going to use my formula up here, which is the PCO2 expected is equal to 0.06 times my change in bicarb from 24. So that's a 42 minus a 24, and I'm getting 0.6 times 18, and that's going to be 10. So I'm going to do 40 minus 10. So 30 is my expected CO2. Here my CO2 is 53, which is higher. So that means that I have a concomitant respiratory acidosis as well. Therefore, my metabolic disease is going to be a metabolic alkalosis plus a respiratory acidosis. Now, that's how you do this problem. Now, I want to make one quick note, and that is in the anion gap, always look for the albumin. So, quick caveat is every decrease in albumin by 1, I'm going to add 2.5 to the anion gap. So what that means is, say I have a gap of 9. So I'm thinking it's a non-anion gap metabolic acidosis, and my albumin is 2. So from 4 to 3, it's a drop in 1. 3 to 2, it's a drop in 1. So a total drop of 2. So 2 times 2.5 is 5. So I add that to the anion gap of 9, and my gap actually is 14. So that's a quick little caveat to remember. But otherwise, this is how I approach acid-base, and I hope you find this helpful. Thanks. For more pearls like these, don't forget to like, share, and subscribe. Thanks for watching.